Hey everyone, welcome back, and today let's solve Leetcode problem 2785 titled Sort Vowels in a String. So just to quickly summarize what the problem statement really says, effectively we're given a string S, and we have to permute S into a new string called T, such that all the consonants remain in their original indices, and the vowels are stored in their non-decreasing order by their ASCII values and placed in those corresponding vowel positions or indices, right? So kind of just a lengthy explanation of what I just said. If you guys want to read through that, you guys feel free to just pause the video and do so. But let's go ahead and look at the examples here. So in example 1, we have our input string S to be L, capital E, lowercase e, T, C, capital O, D, E. In this case, as you can see in our output, all the indices that contained consonants in the input string S, basically non-vowels or non-A-E-I-O-U characters, they all remain in the same indices. So this L was still at index 0. This T was still at index 3, and so on and so forth for the C and D. However, the actual ordering of the vowels were changed. Even though the vowels were all collectively in the same indices, the ordering of the vowels at those indices were different. And they were sorted, in this case, in non-decreasing order by their ASCII values, right? That was kind of the main kind of setup of how these are different, right? And the way that they're sorted is that, as you can see here, capital E is going to have the highest ASCII value, and then it goes to O, and then it goes to E, and then it goes to E, right? They're sorted by their ASCII values. That's going to be the property of only the vowels. And again, have to keep in mind, that's going to be in non-decreasing order or increasing order, right? So it goes from smallest to greatest. So in this case, E would have the smallest ASCII value, followed by O, capital O that is, followed by E, and then followed by the second lowercase e. So in example 2, we have our input string S to be L, capital Y, and PH. In this case, we don't actually have any vowels, or basically any characters A, E, I, O, U. They don't consider Y to be a vowel, they just consider it to be a consonant in this case, and so we don't actually change the order of any of the characters, and so we just output the string as a whole, right? We don't actually encounter any vowels as we iterate through the input string S, and so none of the indices or orderings of any of the characters are changed, hence why the output remains the exact same as our input. So as you can see, the constraints here is the length of our input string S is going to be between 1 and 10 to the 5th power, kind of indicating that we can't have something worse than like an n squared solution or an n cubed solution. It kind of worst case has to be linear or logarithmic at best. And as you can see, it kind of just confirming what the problem statement says. We're guaranteed that S is only going to consist of the letters of the English alphabet and also only of uppercase and lowercase characters, kind of just confirming what the problem statement actually told us and kind of guaranteeing that we're always going to have valid inputs, which brings us to the main kind of solution structure for this problem. And the main kind of observations that you need to really make is that this really is just a direct simulation problem. The problem statement itself kind of gives us the overall structure of how we really solve this problem, and the whole point of this is just translating it directly into actual code that we can deploy to actually get a viable solution. So in this case, we clearly want all the consonants from S to stay the exact same in the exact same order in our output. So we can just iterate over S, and whenever we see a consonant, just directly append it at that index to our output. However, for all of the vowels in the input string S, we can all group them into one list, sort that list, and then add them correspondingly to those corresponding indices that contain vowels in the previous string S. And to kind of formalize that in more kind of formal official text, if you will, of how our algorithm is going to look as a whole, effectively, like I just said, we're just going to scan the string and collect all the vowels, right? We're going to have to preserve their original characters and their original order, and we're going to bump that all, or kind of condense that all into a list, right? Then in this case, we can really just use a sorting built-in function in Python here, because that's actually going to by default sort by ASCII values. So uppercase vowels would come before the lowercase vowels, and which is exactly what matches the problem requirement. And once we actually sort all of the vowels in, or rather from our input string S, we can just build that resulting new string. In that case, they call it T, and that's just going to be by iterating through the input string S, like we talked about briefly before. Whenever we hit a consonant, all we can do is just directly add it at that corresponding index to our output. But whenever we hit a vowel, we have to then pop and consume the next stored vowel in that sorted order, right? To kind of preserve and keep track of that overall non-decreasing order of their ASCII values for all the consonants, but by actually previously sorting that kind of list of all the different vowels from our input string S. And once we actually build that new resulting list, we're just going to join that string into a final, or join that list into a final string and return that final string, right? And so kind of the data structures that we're going to be using, of course, we're going to have vowels, which is basically just a set of vowels, and that's just really just to check for all the membership tests, if you will, and when we are actually checking in our input string S to see if it's a vowel or not, if it actually is in the set, and we're using a set instead of a list for a big O of 1 lookup time, just for runtime complexity efficiency. We're also going to have that list of vowel characters that we extract from S, which we then sort, and that resulting list of characters for our actual output to actually kind of serve as that mutable builder, which we then actually output as our answer. And finally, we're going to have a pointer or index j. That's just going to be like that integer index pointer in our list of sorted characters or vowels from our input string S that shows the next sorted vowel to place whenever we find at that corresponding index as we iterate through the input string S as we're building our resulting list, right? Kind of a common extract, sort, replace, direct simulation approach that we really see in multiple problems similar to this one, right? And again, kind of tying back what the main observation is that because ASCII values actually put uppercase letters before lowercase letters for vowels, like we saw in example 1 here, when capital E and capital O came before lowercase e and lowercase e, we know that sorted vowels would automatically place capital A before lowercase a. And so all we have to do is just sort the ASCII values, and that would actually kind of by default get the problem's requirements of actually sorting them in the correct order automatically by just using Python's direct sort inbuilt method, right, on our list of vowels that we extract from the input string S, which brings us to the main solution for this problem solution. Now, the first thing that we discussed was to actually initialize that vowels set. Again, it's literally just a set to check if we actually find vowels in our input string S of all the vowels, including the lowercase and uppercase vowels. So I'm going to call it vowels. It's just a set of the following elements. It's going to contain the string A, E, I, O, U, and also capital A, E, I, O, U. Right? Effectively, again, all this set is doing is just kind of serving as a membership check. We're checking for different characters in or input string S if they're actually in vowels to check if we have to actually consider sorting them or not. Right? That basically just establishes what we actually consider a vowel and what we're actually checking for if it is in the set to check if it actually is a vowel or not. Right? And the reason why we're using a set is because it's both simple and fast. We know that there's only 10 vowel characters, and so the memory overhead is really just negligible. And also, this does have a big O of 1 lookup time for sets specifically, right? A big O of 1 on average, that is. Now, we're going to get, I'm going to call it VS. That's basically just standing for vowel kind of set, if you will. And the whole point of this is I'm going to use something called list comprehension in Python. It's going to be every character C for every character C in S if C is in vowels. So quite intuitively here, basically we're iterating through every single character C in our input string S, and we're adding it to this list of vowels if it is actually a vowel, meaning if it is actually in this set of all the 10 different possible vowels. So basically what this set is going to contain is basically it's scanning S from left to right, and it's going to contain every character C from our input string S that is actually a vowel in this list. And the characters are kept exactly as they appear, meaning it actually is case preserved. And at the end of this line, basically this VS set, or this VS list, if you will, is going to hold all of the vowels in the original order that we extracted from the input string S using something called list comprehension here in Python, which is really just a for loop inside of a list definition or instantiation. Now, this is where the default sort kind of Python library comes into play. We literally just have to call the sort method on this list, which basically just sorts all the vowels that we extracted from their input string S in this VS list by their ASCII values, right? It's sorting in place, right? And again, this is really helpful because Python's default sort compares characters by their Unicode code point, which is really just the same thing as their ASCII in terms of like standard A to Z and A to Z lowercase and uppercase characters in the English alphabet, which means capital A is less than capital E, which is less than capital I, which is less than capital O, which is less than capital U, which is less than lowercase a, which is less than lowercase e, which is less than lowercase I, which is less than lowercase u, which is less than lowercase O, right? And basically sorting is going to help us yield the non-decreasing ASCII order that the problem statement tells us to do, and so it is actually in the correct order for all the vowels that we extracted from our input string S. And because the set of all the different possible vowel characters is actually really small, in this case only 10, we know that sorting it actually would be really cheap in practice because we have such a limited number of options. However, if the number of vowels in this case, let's just hypothetically say were really large, that's where the heavier work would happen because we are actually sorting, and so it technically would be a big O of v log v, but in this case, since it's only 10, it's not really going to hurt our runtime complexity too much. Now, once we've actually extracted all the vowels from our input string s and sorted them in by their ASCII value in non-decreasing order like the problem told us, now we have to actually prepare our final result as our output. So I'm going to call it result. And it's basically just going to, for now, be an empty list that we're going to actually append characters to build that resulting string as a mutable list, right? Because we know that strings are immutable in Python. And so I'm just going to be using a list to actually append the characters to this list. And at the end, just convert it back to a string or join it back to a final string, which we finally output in the last line here. Now, I'm also going to initialize my J pointer that I talked about in the solution here. And this is basically just going to be that integer index pointer, right? It's going to start off at 0. And basically, it's going to point to the next vowel in our sorted VS list that we have to actually place in the next vowel position or index in the result as we iterate through the input string s whenever we see a vowel. And every time we place and see a vowel in the input in the resulting list, we have to then increment j by 1 to indicate that we've used one more vowel in that sorted order. And here's where we actually start building our input string, or rather our resulting list res, right? So I'm going to iterate through every character in C. So for every character C in S, basically just looping over the original string, that is, we're going to decide for each character whether to append it in the unchanged state, meaning if it's actually a consonant, we don't have to actually do anything with it, or we replace it with the next sorted vowel if it is a vowel from our VS sorted list. So if C is in vowels, we know it is actually a vowel that we have to deal with, right? That means it is actually a U, capital or lowercase, and so we have to actually place the next sorted vowel from the VS list into that actual position, in this specific index, that is. And so we're going to add to our result VS, and in this case, the whole point of J is to be the next possible vowel, right? It's going to place the vowels in the non-decreasing ASCII order in the vowel positions in the output correspondingly. It's basically just appending the jth element of the sorted vowel list in VS to the input, to the final result list res, right? That's the whole point of this J pointer. And of course, now that we've actually used one more vowel that we actually appended to this list, we have to increment J by 1 to move on to the next vowel position to use the following character from our VS list because we've just placed another sorted vowel. What if it isn't even in vowels, meaning our current character C is not in vowels? That means it's just a consonant. If it's just a consonant, we don't have to actually do anything with it. We can just directly append it to our resulting string result, or rather our resulting list res, directly at this corresponding index. We can just append the original character itself and just ensure that that this specific consonant remains at its original indice, right? Because we don't have to actually change it if it's a consonant. And finally, once we do that for all the actual characters in our input string s and update res accordingly, we just have to return our final resulting list res, but we want it in the form of string. And so in Python, I'm going to actually use the .join method here and just join this resulting list back into a string of characters in that changed final correct order. So on this I made in the syntax 00, there should be accepted and there should be a valid solution. And as you can see, this really is just about as efficient as you can get it to be, right? And again, keep in mind this result is really just that permutation of S where the consonants stayed put in the corresponding same indices, but the vowels are placed collectively in the same indices, but in a different ordering based on their sorted ASCII order, based on the VS list sorted list, right? And again, another observation that we can really quickly make, if there are 0 vowels, that means VS would be empty. The code would never actually use VS at index J. And so we'd simply just append all the characters unchanged to S because they'd all be consonants. And an example of this was actually example 2, where we didn't have any vowels. We only had consonants, so we didn't have to make any changes. In this case, our VS list would be empty because we wouldn't actually find any vowels as we iterated through the input string S, and so there would be no changes to be made. But of course, example 1 did actually have changes to be made based on the 4 vowels that we did have in our input string S, right? So, on a high level, how again are we really solving this problem? Effectively, we're first identifying every single vowel in the input string S, and then storing it after we extract it from our input in this VS list. Then, we're actually sorting this vowel list that we extracted from our input by ASCII value to actually determine the final order of vowels we have to actually put in the output for their corresponding indices from the vowels in the original input string. Then, we're simply initializing our pointer and our resulting final string, and then rebuilding that string by first iterating through the input string s. And for each character C in that input string s, we're first determining if it's a vowel. If it's a vowel, we have to append the next character from the sorted vowel list that we got from the J pointer in VS. However, if it was just a consonant or not a vowel, we'd simply append it unchanged at that same index. And finally, once our loop actually completed here, as you can see, we just join that list back into a list, or rather a string of characters, to just combine the ordering correctly. So we'd have all the consonants saying unchanged positions and all the vowels in their correcting order, right? Sorted again by their non-decreasing or increasing ASCII values, right? And again, it is a very common clean, or rather extract, sort, and replace pipeline, right? We're just extracting vowels from our input string s, we're sorting them and replacing their order while keeping the consonants indices exactly the same, unchanged, right? Which brings us to the memory and runtime complexity for this solution. So the runtime complexity here is going to be an overall big O of n log n. N is going to be the length of our input string s, and v is going to be the number of vowels in our input string s. Why is that? Well, because to actually extract all the vowels from our input string s, as we saw here in line 4, that would be big O of 1. Big O of n rather, because it's really just a single for loop here, or a single iteration or pass of our input. To actually sort the vowels, it would actually be big O of v log v, and to rebuild that result is another big O of n. So overall, it would be big O of n plus v log v fully simplified, and in the worst case, we know that v would simply just be big O of n if all the characters are vowels. So the worst case runtime complexity would be big O of n log n, kind of like our upper bound or our bottleneck fully simplified official runtime complexity. And that brings us to our memory or space complexity here. That's really just going to be a lot more simple. It's just going to be big O of n. Why? Because we really just use this extra VS list, which is going to be a force big O of n, if considering worst case, all the characters in our input string s are vowels, right? Technically, this is also taking up space, but since it's always a guaranteed 10 characters, it's not actually going to impact our memory complexity, because we don't care about coefficients and constants, because they don't actually really affect our complexities in general, right? So the overall extra space or auxiliary memory or extra data structures that we use is going to be linear or big O of n. And again, really just tying back to that main overall observation that we have to make. Because there are only 10 distinct vowel characters, the capital and lowercase a, e, i, o, u's, an alternative would actually be counting specialized placement, like bucket sort over those small vowel alphabets to actually achieve big O of n runtime in practice as well. But that isn't really too problematic, because we really only have 10 possible characters, and so that wouldn't really affect our runtime too much. And so it really is just about as efficient as you can get for typical constraints here, right? So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.